Okay, so I just want to introduce Bogdan Zisu, who is a colleague of ours who's works in the manufacturing business called Spray Systems Australia. So Bogdan is in the well, he'll explain what he is, but I just want to thank him for coming and doing this. We had hoped to have him face to face so we could get talk to him more directly about the system that they offer. But as the context here is that in Canterbury particularly, we're looking for other manufacturing options for sheep dairying, and I guess the question is whether or not a cheaper, more sort of specialist dryer system, which I think that Bogdan's company manufacturer might be an option for the industry in that location. So over to you, Bogdan. If you could share your presentation, we'll get started.
Thank you for the introduction. So my name is Bogdan Zisu. I'm streaming to you from Melbourne, Australia, at the Fluid Air from the Fluid Air facility. I was introduced as being part of Spraying Systems, and that's correct. Spraying Systems is the actual parent company, and Fluid Air is the division that we're going to be presenting to you from today regarding electrostatic spray drying. So the idea behind this presentation is to actually provide an introduction to you on this technology. It's a fairly recent technology, and it pretty much is an alternative to existing spray drying capability, and it gives us the ability to dry at very low temperatures. So we're drying liquid streams to a final powder product at much milder temperatures. So how do I see this? How do I actually see this in terms of existing capability? Well, if we look at on the bottom of the slide, I have a temperature scale. So if we look at the far end, on the high temperature end, we've got traditional high heat spray drying. It's a very effective technology. It has the capacity to dry a lot of product. Now, we're talking about tons of product per hour, and that's all good and well if your product can tolerate fairly high temperatures. Now, if your product is heat sensitive, the mainstream alternative is to look at the opposite end of the temperature scale, and we're not talking about freeze drying. As the name suggests, we're freezing the product, and under vacuum, we're removing the moisture. Very good technology, very effective in preserving biological activity. However, the limitation with this technology is that it is a batch process. That means, depending on your batch size, you might have a product up to 2, 3, maybe even 4 days of drying. So there's a huge gap in between these two existing established technologies, and this is where electrostatic spray drying fits in. So it gives us the ability to not only produce product in a continuous operation, but it also allows us to dry material at fairly mild temperatures, well, in comparison to high heat spray drying, and therefore we can retain some of the biological activity that's often lost in high heat processing. So just one actual slide on the commercial aspect of things. This technology became available as a polar dry range of dryers. It became available sometime about 10 years ago or so, released in the US, expanded to Europe, and more recently Australia and New Zealand. So the current lineup of spray dryers stems from the very small 0.1 model, where you can remove from up to 100 or 0.1 kilograms of water per hour, to the largest dryers that we have that are available at the moment, which is the 200 kilogram per hour capacity, which is a 4 chamber design. So enough on the capability at the moment. I really want to do today is actually give you an introduction to the technology, explain to you how it works, what it actually is, and to put it into context of milk processing. And I apologize that I don't have actual sheep milk data, so we're going to have to rely on bovine milk in the examples that I'm going to provide. What I'm going to do is actually focus on 3 key aspects that I believe make it unique, what makes electrostatic spray drying unique. The first is the ability to dry at low temperatures. The second is to highly control agglomeration during the drying process itself. And third, this is something very interesting, especially from a protein chemist, it's the ability to stratify macronutrients in the atomized droplets. But first of all, let us begin with low temperature spray drying. So what we have in front of us is a schematic of what represents a single atomized droplet. This single atomized droplet will eventually become a single powder particle. Now, on the left, we have a very simple a schematic of showing how how these powder particles are dried in a traditional high heat spray dryer. And on the right, we have electrostatic spray drying. In both instances, on the y-axis, we're looking at the droplet temperature. X-axis, we're looking at drying time. What we see in the traditional high heat spray drying is that we have two distinct periods of drying. We've got the constant rate drying period, and at some point we transition to the falling rate period. Now, in the constant rate period, we notice that the droplet temperature remains fairly low. At this point, the droplet is very moist. We have a lot of water that's being evaporated, and this evaporation gives a cooling effect. So it prevents the droplet temperature from drying. However, as more water is removed from this droplet, we lose that evaporative cooling effect, and this is the point where we transition to the falling rate period. What happens is that we're now exposed to very high temperatures. Let's say traditional high heat spray drying inlet temperatures 180, maybe 200 degrees Celsius, is that we form a shell, a hard shell around this atomized droplet, but the core is still filled with moisture that needs to be removed. And the only way that this can be done is by using temperature. And this is where the droplet or the powder particle temperature increases. And once we reach usually about 60 degrees Celsius, that's where we start to lose a lot of biological activity, especially in milk proteins and enzymes. Now, if we look at the electrostatic spray drying curve, we see that most of the drying occurs in the constant rate period. This is done by actually introducing an electrical charge at the time of atomization. And what we, just to put it in simple context, what we're actually trying to do is actually separate the active components, the polar and non-polar groups within that atomized droplet. So what in effect we're doing is actually pushing that polar component, the moisture, to the outer edge of the atomized droplet, which then allows effective and efficient removal of water at much lower temperatures. Now, let's put this into context. Spray drying milk, bovine milk, apologies, not sheep milk. In a traditional spray drying operation, inlet temperature, there are two temperatures that we need to be mindful of: inlet temperature and the outlet temperature. Inlet temperature is actually the temperature that the liquid is actually dried. It's the temperature of the drying chamber, usually around that 180, 200 degrees Celsius mark. Now, the outlet temperature is actually very important itself. This is actually the exhaust temperature, and the reason this is important because the product temperature, the temperature of the powder closely resembles this outlet temperature. It doesn't usually get as high as the outlet temperature, but it often exceeds 60 degrees Celsius, and this is where we have thermal denaturation. Now, in electrostatic spray drying, we work at much milder temperatures. Now, in addition to the inlet and outlet temperatures, we do have other parameters that I will introduce shortly. But inlet temperatures, maximum temperature that we can dry is 150. But in terms of proteins and biological materials, we generally stay at around 80, 90 degrees Celsius inlet. And the critical element is the outlet temperature. At these temperatures, the outlet temperature is somewhere between 30 and 40 degrees Celsius. And the product temperature is therefore even lower. And we're actually staying well below that 60 degrees Celsius temperature, which is the denaturation point of many heat-sensitive materials. In addition to these two temperatures, we also have an additional atomizing temperature, which actually helps in controlling the outlet temperature. But most importantly, we have an electrostatic charge, as I mentioned earlier, which gives us the capacity to stratify the macronutrients. And I'll talk about this in slides to follow. But in either case, regardless of the inlet and outlet temperature, regardless if we're using traditional high heat spray drying or electrostatic spray drying, we end up with a powder that is very low moisture content, usually below 4%, and very low in water activity, usually below 0.2. Okay, this obviously opens the door to processing a lot of heat-sensitive materials. Put it into context of milk drying, this can be applied perhaps to colostrum, lactoferrin, or other high-value milk products such as infant formulations. And I know that there are government restrictions on HPP, high-pressure processed milk in New Zealand, but there is an opportunity, at least here in Australia. For those that are working with microorganisms, again, a sensible alternative to freeze drying. Now, just one slide that I'd like to present to you in terms of preserving bioactivity in terms of low temperature spray drying. I've included here an example of active bovine lactoferrin. Testing for bioactivity was independently done through Ag Research in New Zealand. So this is a laser testing method. I'm not all that familiar with the testing method myself, but basically, to put it in simple terms, it detects only the active form of lactoferrin. So if we do have thermal damage to the lactoferrin, it will not be recognized by the antibodies. If we look at the results, we have a very mild heat treatment here on the left, the red bar. Spray dry at inlet temperatures of 150 and exhaust at 60 degrees Celsius. We do have some loss, about 10% loss in this lactoferrin bioactivity based on 6 milligrams per mil assay, whereas the two electrostatic spray drying powders that we generated at inlet of 90 degrees Celsius and 30 degrees Celsius, we have very, very little to no loss of this biological activity. So, at the time, I'll move on to the second aspect, which I regard as uniquely electrostatic, and that's the ability to control agglomeration during the drying process. What does this actually mean? When we atomize, we can actually control we can pulse the electrical current during the process of atomization. What that means is that we can pulse on, we can pulse off. And in effect, what we're doing is charging some of the atomized droplets, and we're not charging others. So taking the principle of electrostatic spraying, these charged droplets will naturally attract to a ground or uncharged particle, and we have natural occurring adhesive forces within the dryer. And depending on the electrostatic charge, how powerful the charge is, we can to some degree control the average agglomerate size. And when we talk about agglomerates, these are actually very large powders that we create, powder particles. If we look at the photos, these are actual photos that we've taken, we haven't zoomed in, of a whole milk powder. So it looks like extremely large particles, but it's actually agglomerate, and I'll show you that in the next slide. But I also like you to pay attention to the color of the milk that we've dried. It is extremely white. It retains that milky white characteristic, and I'll talk a little bit about it in a later slide. But now back to the agglomerates. And what do I mean about agglomerates and size? And what we have in front of us is a scanning electron micro image of spray dried powders on the left, electrostatically spray dried on the right. The top images are going across. We have magnification at 500 times, and we zoom in 5,000 and the bottom images. What the clear distinction between the powders are is that, first of all, electrostatic spray dried primary particles are generally smaller. And if we're looking at the zoomed particle, there's a lot of agglomeration, whereas we see very little to no agglomeration in a traditional spray drying process. So let's put this into practical terms. What does this actually mean for processing? Well, in traditional milk processing, dairy milk processing, or cattle milk processing, bovine milk processing, agglomeration is actually practiced to create instant powders. That's the ability to hydrate in water immediately. So this is usually done as a second processing step, usually for a fluidized bed agglomeration process after the powders have already been dried. Now, not only do we achieve this agglomeration in the dryer itself, so that we don't require secondary agglomeration when electrostatically spray drying, but we can also change the polarity. So we can actually reverse the polarity of our charge. So we can create a combination of very rapid hydrating powders based on agglomerates and charge, or we can have the opposite. If you, for whatever reason, manufacturer wishes to have low solubility in the powders, we can also create this by minimizing agglomeration and reversing the charge. Just to give you an example, put this into perspective, on the left we have a starting material, a dairy material. It's actually colostrum, which was highly agglomerated with the charge that allows hydration, and we compare that to the same material which we had a high reversed agglomeration, and we can see a huge difference in terms of hydration abilities. All right. All right. Probably running out of time, so very quickly I'd like to move on to the third element that I believe is uniquely electrostatic spray drying, and that's stratification of the macronutrients within the atomized droplet. So what do I mean by this? In an atomized droplet, these atomized droplets, of course, become an individual powder particle. In traditional spray drying, we have a random arrangement of the macromolecules as well as the water component. And when these are dried at high heat, there's a natural tendency for the lipids to actually congregate on the surface of the particle. This is a well-known phenomenon. But in electrostatic spray drying, although we can't completely eliminate these natural forces, we do have some control to minimize this effect. So what we're doing is charging our particles or macronutrients based on polar groups. So we're just put it into very simple terms. Let's say we're bringing the active material to the core of the droplet and pushing the polar component to the outer edge of the atomized droplet. And what does this actually do to the surface composition? Let's have a look. So if we focus on the bulk composition of a full cream milk powder, what we see is that carbohydrate, in this case obviously lactose, is very high, and fat, although fat is high, is a lot less than carbohydrate. But when we look at the surface composition, this is a well-known fact, that fat always overrepresents the surface composition in a spray-dried powder. And although we see the same effect in electrostatic spray drying, by introducing the electrostatic charge, we can actually minimize the amount of surface fat on the composition, which can, in time, potentially increase the shelf life by inducing oxidative stability and slowing down the rate of caking or hardening of the powder. Now, on the very last slide that I have to present for you in terms of full cream milk powders, I'd like to draw your attention to color. So in a previous slide, I mentioned that we have a very milky white powder after electrostatic spray drying, and we can actually put a quantitative value on this by looking at LAB values. So if we focus on the B values in this electrostatic spray dried products, B values, I guess an increase towards the B direction indicates that it's going towards the more yellow color characteristics. So yellowness, we see that spray-dried powders are more yellow than the electrostatic spray drying. And this is actually visible. It's clear to the eye when you actually compare an electrostatic spray-dried powder with a high-heat spray-dried powder. Now, the other interesting result is that if we actually put this powder in an oven and we heat it at very high temperatures, exceeding 100 degrees Celsius, to induce browning, we can also see that browning reactions are also at least reduced in electrostatic spray drying compared to your traditional high heat. And although I don't have the data to back it yet, something that I'm working on, this is generally an indication of accelerated non-enzymic reactions. So this is the beginning of Maillard reactions, which not only reduce the shelf life of the powder, but can also potentially create bitter compounds. Okay. So just to wrap it up, I apologize, 15 minutes is not a lot of time, but basically what we have now is a scalable, continuous technology that allows spray drying to take place at very mild temperatures, obviously making this technology suitable to drying heat-sensitive materials by preserving biological activity. In addition to biological activity, the powder characteristics, or the powders that we actually generate, also have unique physical and chemical characteristics. So having said that, I thank you for your time, thank you for your attention. And if you have any interest, and if you'd like to learn more about the technology itself, or even if you like to wish to take the extra step and perhaps even dry some of your products on our pilot scale dry here in Melbourne, please feel free to contact me. So thank you very much.
Fantastic. Thanks very much, Bogdan. That was it's really full, and I'm sure people are really interested in the possibilities of this. Can I just a couple of questions? What kind of can you hear me at all?
I can't see you. Apologies, but I can hear you.
That's right. That's fine. So what kind of uses are being made of this technology now, and what would be the on the larger end of the the machines, what would be the kind of cost per kilogram in terms of production? Because obviously we're inevitably sheep milk is in the higher, we want to be 20-30% above the value range of existing products, but we want to be very specialist products. So it's kind of interesting to know what specialist products are being currently produced and what kind of cost per kilogram we're looking at.
Absolutely. And I'll try and answer some of that as best I can. And some of these questions, especially about the cost, are very specific, but I'll try and generalize it as much as possible.
Thanks.
So the technology itself, I guess we're coming up to 8+ years since it was developed and released in the US for the first time. Similar to the US, Europe, and Australia, which has only been a technology that's been available for the past year here. It's the markets that have that we've actually made most sales are emulsions, which I didn't speak about, and bacterial applications. So it's been preserving biological activity. We are, however, especially in Australia and New Zealand, where we've got a lot of dairy, a lot of bovine, sheep, not as much sheep and caprine milk. We're trying to break into that market as well. And we know it does very, very good things for biological retention of biological activity. So although the main markets so far have been preserving bacteria as pretty much an alternative to freeze drying, I believe it's also very suited to processing things like lactoferrin because of the high return value, and it's also freeze dried at the moment. So this technology, it's very hard to put a price tag on. Unfortunately, the technology, the capital isn't cheap as is the case with most capital investment. But just to generalize, and in terms of products, I really, if there are any specific questions, I'm happy for you to direct the question to our sales guys. But from what I understand, based on quantity produced, we're not in the same ballpark as spray drying. That's an obvious. That's a given. Just the amount of product that they can produce is far exceeds us. But in terms of spray drying, because of our ability to produce product in a continuous manner, we're probably about half the processing cost of freeze drying. So this is just a generalization. Obviously, it depends on the product characteristics, what temperatures we can dry at, and how much product we're producing.
Right. That's a good. That's a nice comparison, actually. That's very helpful, because most people in that area will know broadly what the cost of freeze drying is, depending on the scale of the freeze drying technology available. So yeah, that's helpful. Thank you. One question from someone in the group. In terms of the cost and time and cost required, is there much difference in the time and cost between the two methods, traditional versus electrostatic? So there's a timing issue that I didn't pick up on. Does that make sense to you?
I'm not sure exactly I understand what is meant by time, as in how much can we produce, perhaps?
I guess it's down to the kilograms per hour, but is there any timing constraints, or is there a speed? I'm not quite sure what that means. Maybe
perhaps yes, perhaps if it can be rephrased. But if I'm thinking along the lines of the questions directed, it is based on drying capacity. So we're obviously a lot smaller at the moment. We can remove up to 200 kilograms of moisture per hour. That's quickly where the company's developing much larger dryers. I think at the moment they're very close to a 500 kilo per hour, and they're also working on a ton per hour. But that's probably at least 12, 18 months away at least.
Sure. Okay. No, that's cool. No, that's helpful, and thank you very much for the cost comparison, because that actually does a lot of. That's very helpful, because I know a couple of people around New Zealand have explored freeze drying, and certainly being able to cut the cost, which is very expensive, obviously per kilogram. Would be interesting to contact you and at least explore that a little bit further. So that's very helpful.
Absolutely. Do you mind just add a little bit more? Something that I overlooked in the presentation is actually very critical, both cost and processing. We actually dry in a nitrogen environment, not an oxygen environment. Obviously, that adds processing costs, but if we have a highly oxidative product, high fat, or an anaerobic bacteria, it has significant benefits as well. So that's something to keep.
Cool. Great. Hey, thank you so much for coming on and doing it in this environment. I hope everything's going well for you in Australia. That you did mention the other day that as a food processing manufacturer, you're in essential services. So the reason why you're in the office and not at home is because you're in that space. So appreciate the time today.
Thank you very much for the opportunity.
Thank you. So if you want to share your presentation with me, I'll put it up on the website and we'll get that out to people. Great. Thank you. So I just want to switch over to Jolin Morel, who many of you will know from previous conferences and the work that he's been doing. So he'll explain what he's doing, and over to you, Jolin.
So as Craig said, I think a lot of you have seen me before talking at these conferences. So I'm discussing the work that we're doing on the science and application of freezing sheep milk. And this work has been done at Massey University as part of the FIAT program. That's a Ministry of Business Innovation and Employment funded program aimed at increasing New Zealand's export earnings by the application of new food technologies. So we all know a little bit about the background of the New Zealand sheep milk industry, I guess. And we know that we've got from a wide range and different sizes of farms, from 60 to 80 sheep in one unit to over 2,000. We don't have any established body like Dairy Goat Co-op or Fonterra, but there is a lot of room to grow. And in order to do this, some of the smaller operators would ideally be able to collect several milkings and then ship that product all at once to reduce shipping costs and be able to reach larger processors. So what has been done occasionally is freezing, and our project was started to develop a more robust, reliable on-time freezer to let new entrants get into the market. So as it's currently done, freezing is often done in big bladders or buckets and put inside a commercial chiller. And there are some issues with this. It's quite a slow freezing process, which can lead to loss in quality in the fats and the proteins in the milk. And there have been a few proposed explanations for this. One of the main ones is that lactose acts as a cryoprotectant, and that stops milk from degrading, or the proteins in the milk from degrading during frozen storage. But during slow freezing, this can often crystallize out, reducing this protective effect. Slow freezing also has large ice crystals, which can force the proteins and fats together and also damage fat globule membranes, leading to increased fat boiling off and oxidation effects. And another major one is that when we freeze something, we end up with a more concentrated phase remaining. And this concentrated phase has got lots of salts and different changes in pH, and this can lead to the proteins in the milk aggregating and collapsing out. And another really big one, which we've been looking at the last few months at Massey, is that if you have a large bucket or bladder, it's very slow to thaw, and this slow thawing can lead to bacterial growth as you're heating it up again, which is not great for milk quality. So one of the things I looked at was the effect of different storage conditions on the milk quality. And one of the major effects I found was that the temperature at which you store it is quite critical. So if we store milk at minus 10 degrees frozen, we end up with a gel forming after several weeks of storage. And we can see this in images A here and in the top here, where we've had a gel that's formed after storage at minus 10 degrees, but the milk that's been stored below minus 25 hasn't separated at all, as you can see here and here. We also see this if we look at the average particle size in the milk. So this red line shows the average particle size in milk that's been stored at minus 10 degrees, and we can see it increases a little bit after 4 weeks and dramatically after 8 weeks. And we can also see this dramatic increase in the evolution of the particle size distributions. However, as I said, at minus 18 or minus 25, we have seen very little aggregation occurring. Another change that occurred during the frozen storage was that the calcium concentration in the serum phase, or the not in the casing micelles, changed during the storage period. And this change is greater in milk that was stored at higher temperatures. So milk that was stored at minus 18 and minus 10 degrees, as you can see here, the calcium concentration in the serum phase decreased significantly, showing that it was going into the micelle phase. Whereas at minus 8 and minus 28 degrees, there was no significant change across the storage period. So to understand why these changes are occurring at different rates at different temperatures, we can go back and look at, say, phase diagram, which describes where the water, or what phase the water in the milk is in at different temperatures. And this is a phase diagram that I constructed from differential scanning calorimetry measurements of ovine milk. So basically, we see that if we take milk and freeze it, cool it down, and freeze it, we have first a mixture of ice and freeze concentrated milk. Then as we get colder, the solution becomes too viscous for ice to continue forming, and we end up with a glassy mixture of ice and a glassy concentrated milk. If we look at the composition of the milk during this process, the unfrozen liquid phase, we can see that the greatest change happens between, say, minus 0 degrees and minus 10. However, this is the amount of solid in the milk. However, from minus 10 to minus 25, this change is not as significant. Same with the lactose in the milk. It increases greatly to minus 10 degrees and becomes supersaturated about minus 2. And then there isn't a huge increase afterwards. Yet we saw a large difference in the storage behavior between these milks. And that, I believe, is largely due to the viscosity increase. So as we get closer to that glassy state, the milk becomes significantly more viscous. And we can see that the viscosity of the milk at minus 25 degrees is several orders of magnitude higher than it is at minus 10 degrees. And this slows down any reactions which occur to cause the proteins to knit together or the fat to oxidize, along with also effects from the decrease in temperature, which also slows down reactions. So that's a bit about how the milk behaves during storage. And one of the other things that we looked at was how the morphology or the ice structure changes during the freezing process. And one of the things that was interesting when looking at some micrographs of frozen milk is that milk that was frozen slowly showed some lactose crystallization. And we can see that we have some small crystalline structures, roughly 400 nanometers in size, which we saw in milk that was frozen slowly, but not milk that was frozen rapidly. And I believe the reason for this difference is that if you freeze the milk slowly, we have a long time where the system is has a low enough viscosity for lactose to crystallize. But if you freeze it rapidly, the system becomes viscous too quickly for the lactose to crystallize, so it remains in the state which in the unfrozen phase, which allows it to protect the proteins, etc. So looking at some more differences between rapidly frozen and slowly frozen milk, we can see on the left-hand side here, I should say, milk that is frozen rapidly, and we see thin bands of concentrated solutes and thin ice crystals, whereas milk that was frozen slowly has great big ice crystals here, and a very thick band of concentrated milk solutes, or milk proteins and milk fats. And what this means is that if we do have any aggregation of the milk, that these particles will be much larger in slowly frozen milk than it should be in rapidly frozen milk, and this can be both detected as maybe a possible grittiness, because you can taste gritty particles or notice gritty particles for soft ones above roughly 80 micrometers in size, and also possibly a higher rate of sedimentation. So as well as looking at what the ice morphology was in the frozen state, I also looked at how the freezing speed affects the ice morphology. And I looked at this in basically a mixture of the salts and sugars that are seen in milk, and a mixture of in the whey proteins, or basically the whey phase, so no casein micelles, and skim milk and in whole sheep milk. And what these images basically show is that we have, as we increase the freezing speed, we go from a flat planar freezing front to form columns and dendrites, and effectively into a final dendritic form at high freezing front speeds. And what this means is that we can capture in the ice matrix all the various fats and proteins, etc., and we don't have a gross separation of components like we saw on that slowly frozen, on the images of those slowly frozen milk. I was able to plot a map of these behaviors against freezing front speed and milk components, and what we basically see is that the interface becomes more complex as we increase the speed and as we increase the number of components in the milk. The interface also has a very regular spacing, which can be, which is strongly related to the freezing front speed. So that was a little bit about the science, and then we went to how to apply the science to build an on-farm freezer, which was kind of freeze the milk rapidly with minimal handling required, that would be simple and robust for an on-farm application. and we'll create a product which is easy to handle and easy to thaw at the end. So to do this, we went for about 3 generations of freezer. Our first generation was a rolling droplet freezer, which I mentioned at the start, my first couple of presentations at this conference. Then we looked at the falling film flake freezer. And now we have our 3rd generation freezer, which uses a novel technology exploiting some of the behavior that we observed during the freezing process. So this 1st generation freezer, it basically exploited some of the new surfaces that are coming out which don't wet. So the idea was that we would roll droplets down a surface against a cold airflow, and they'd freeze in a little form of hail. And we expected that this would be compact, give a rapid freezing, good product quality, and have a free-flowing powder-like product, which would be easy to handle and thaw. And we tested this on a single droplet scale. And this is a series of images that we took of water that was being frozen, going from a small droplet to a frozen droplet in roughly 40-odd seconds. However, as we developed this further, we found out that it would be very expensive to build, and there were certain conditions under which these surfaces would cause the liquids to stick onto them, which would then cause the whole thing to block up. And that was sort of an unavoidable condition which just happened periodically. So we moved away from this onto our falling film plate freezer. And this is adapting some equipment that's used in the ice making industry. So basically the idea is we have a cooled surface which we spray or distribute the milk onto. It would freeze onto the surface, and it could then be removed by either a scraper or by adding a little bit of heat to melt back a bit and have it all fall off. So we built our prototype unit, as you can see here, trialed it with water and with ovine milk. We found that even at high freezing rates, we'd still have a little bit of freeze concentration occurring, so we had a little bit less milk solids in the ice versus in the liquid. And that water ice and milk ice behave significantly differently. So milk ice is more cohesive than water ice and wouldn't be removed by a little pulse of heat like water ice was. So we had to modify our system with a scraper. And as we were doing that, we basically came up with our final novel freezer. And another issue with these falling film freezers is that we have got a basically free surface of milk which is exposed to air. And this is not great from a food safety point of view, and was something that we wanted to remedy with our final 3rd generation freezer. So this one here uses some novel principles of the freezing process that we found during our research. It's continuous. It's a very simple process. It's very food safe and requires minimal interaction by the operator, and has an easily handled product. So the things that come out are basically regular pellets, which you can easily handle as a bulk and then put through things like continuous freeze dryers, etc. And we found that it's been applicable well beyond milk. We've trialed at least 8 products, including things like kiwi fruit pulp and orange juices and other food products, liquid food products on it, and it's performed beautifully for everything so far. And we're currently commercializing it. We're actually applying for our final patent application today, but as a result of going through the patent process, all I can show you of what it looks like is basically this. It's a black box. We'll be able to show you more, hopefully, very soon. And so having this, we also discussed what this would look like on a as sort of a full process or a logistic process. So we have both plans for items that can be put on farm, as seen here, and then transported to a final customer, or something which is then transported to a central location at, say, for a co-op of several farms, where they freeze it all together and then can send large quantities off to a final processor. So that is our update on where we are at with our project. Thank you for listening, and I'm happy to answer any questions.
Thank you very much, Jolin. That's great. So just can you just give us a quick update on where the prototype is currently? So
our prototype unit is currently at the commercialization partner. I'm not sure how much I can say about where they're at. But they are currently working on it and running through a series of trials, and then looking to get our little lab scale or lab prototype cobbled together into a full commercial unit, which can then go onto a farm. And they have been working well, or at least up until this past little blip with everything being shut down.
Yeah. No, I particularly like your black box presentation. It was not particularly illuminating, but I appreciate the conditions under which you're working.
Yeah, unfortunately, as the conditions are at, I think we heard back from the lawyers yesterday that the final application will be filed today for that patent. So, yeah.
So
well,
just a couple. Sorry, you go.
Just maybe next year you can share some more information.
Yes, I've got a lot of nice information and nice graphs and nice other things which I'd like to share, but.
So just there's a question from YouTube. Do all milks behave the same?
So we've trialed it with cow milk, with our particular system we've built with ovine milk and cow's milk, and at a range of different concentrations, and with some adjustments in terms of operating conditions, it's operated well for all of them. We've also tried it with cream as well, and our system has worked beautifully for them all.
Okay, and so have you had any contact with MPI or some of the producers, for example, around whether they would be willing to look closely at the product, which the output product as a basis for their own processing?
So in terms of MPI, we have done a little bit of work with them. I'm not sure, but it has been promising. But of course, I can't say, I don't want to put words in anyone's mouth or say too much at this point. And there are some producers who are also talking to our commercialization partner. So I guess that is between them and the commercialization partner where they're at with their development.
Can you hear me, Craig?
Yes.
Yeah, just a quick question from Rod McMillan here in Springston. Great technology, and looking forward to the commercial translation of that. Where it comes to verification by MPI that the freezing and thawing process is verified, are you guys going to do that, or does every farmer have to do that in their own situation and get an RMP plan, etc.?
I believe our last discussion of this is that it would require possibly a modification to current RMPs that we have. We are doing, as I said, some work with MPI looking at the safety of various milk freezing methods. And we are just finalising up that work now. And I guess that this is them looking at a way of incorporating freezing, into sort of the on-farm practices versus processing, which it currently is.
Just a supplementary question, because the more effort you guys put into that, the more that can help us, sort of a leverage game, really. Instead of 20 farmers going out and convincing the keyboard warriors in Wellington that it's all good.
So as I said, we have done some work with them. Once again, I don't want to put my foot on it by saying anything I'm not meant to.
Yes.
But so they are aware of the application of freezing to sheep milk, and I believe possibly other milks, and it is something that they have proactively looked at currently through us. So
okay. If we can help out, let us know.
Great.
Cheers.
So by the sounds of it, this work will continue, both in terms of being able to share some more of the black box with us, and also the regulatory. So we'll invite you again next year to to talk about the updates.
Just a quick last final question. A group of farmers might invest in this, but what kind of pricing are we talking about, Jolin?
So I do have the numbers somewhere off there, but not on the top of my head. But we don't think it would be, we don't think it should be prohibitive. We don't have any particularly exotic. I mean, while the new technology is novel, we have managed to, reduce any sort of exotic fabrication, etc., required. So it shouldn't be too horrible. But yeah, I don't have the numbers off the top of my head at the moment.
That's fine. Okay, brilliant. Thanks very much for your really in detail. I love your background, by the way. Is that a ice particle?
Yeah, there is a fat globule in some milk that was frozen in liquid nitrogen.
There we go. Looks cool.
With some casing micelles and everything wrapping around it.
Fantastic. Okay, thank you very much for that, Jolin. And we're probably just going to take a little lunch break now, actually. I think that's time for lunch. So we'll resume at 12:45, which is in just under, maybe just on 20 minutes time, with the session from, Linda will be chairing that session on nutrition. So it includes Amber Milan from Auckland University. We're talking about the findings from the Shindig, that's the human clinical trial work. Natalie Orborn on the desk work, some work from the Ritter Institute on digestion, and then on the A2 beta casein differences between sheep and cow. So really good detailed scientific program coming up in early in about 20 minutes time. And thanks very much for hanging in there, everyone. I know some of this is sort of fairly technical data, but we're trying to get this out to people so that they can get something to mull over and think about in terms of their own particular challenges and problems you're engaging with. So I think we're back to about 130 people, which is really good to see. So we'll be back in about just on 15 to 20 minutes time now, and I look forward to seeing you then. So hope you have a nice sandwich or something for lunch, and see you shortly. Thanks very much.